everyone. I am everyone Ercolesi, and I'm happy to present a paper we had with my collaborator Sebastian Gans. And the paper is about reviewing the true cost of locally differentially private protocols from an auditing perspective. So to start with some context, we saw already many types of audits from the keynote of Natalia this morning, from the previous talk, and what we can conclude is that they are the backbone of accountability and trust, because we can somehow make some form of systematic review of the system, of model, to ensure the compliance with standards and the achievements of objectives. So you can imagine this is widespread from many industries. It's not about only privacy, it's in healthcare or accounting and finance and so on. So the motivation from privacy auditing is, here is a non-exhaustive list. We can use it to uncover vulnerabilities to further prevent privacy breach or other privacy incidents. We can also use it to ensure compliance with data privacy laws, as we saw in the keynote this morning. We can also use it to evaluate the robustness of the privacy model we have, such that we can test it against the state-of-the-art attacks. So why do I mention privacy attacks? We can use it because it's a way to ensure that we detect the vulnerability of current privacy techniques to the state-of-the-art attacks. So for instance, we saw some papers about identifying the failures of pseudonymization and further inventing key anonymity. And later on, we saw some paper proposing some attacks, like homogeneity attacks, to key anonymity methods and further inventing ad diversity. And so on, until we arrive at some point with some reconstruction attacks to aggregate the statistics, which inspired the invention and adoption of differential privacy. So we all know a bit what is differential privacy, and what we'll be talking is about the local model of differential privacy. So which means that the differential privacy model is moved to the user's device, which means that we are protecting from different data points. So we can imagine to any input v and v prime in the domain of the mechanism, and we have any output z. We want that the ratio between these two probability events to be bounded by e to epsilon. So bounded means this corresponds to a theoretical upper bound. So many works in LDP will try to propose a new LDP mechanism such that they comply with these provable upper bounds. So some audit questions that may arise is that, are these bounds always tight? Or for instance, can we get some form of empirical privacy for a mechanism when we use state-of-the-art attacks? Or even if we don't have some formal proofs for an LDP mechanism, what happens if we try to estimate some form of lower bound? So this is the role of differential privacy auditing in the literature, which is some form of, for instance, had been used to assess the tightness of a differentially private mechanism. And tightness means that the practical or empirical epsilon will correspond almost match the theoretical epsilon. Or in some cases, it can be used to assess the empirical privacy. So in this case, we are using real data points, which are not always worst case. So which means that the empirical or lower bound epsilon will sometimes be smaller than the theoretical epsilon that we have. Or in some cases, it can also be used to detect bugs, because not all privacy proofs or implementations are correct. So whenever we detect that the empirical epsilon is higher than the theoretical epsilon, this corresponds to a bug. So now let's move on to how to audit local differential privacy. But first of all, let's remember how to audit differential privacy. So we saw from the previous talk that we can use some form of a membership influence attack in centralized differential privacy. And in differential privacy, we consider two neighboring databases that differ on the data from a single person. So the distinguisher is basically trying to infer, has this computation being on the database with my target on or not. So we can formulate differential privacy as some form of hypothesis testing. So for the attacker is basically trying to infer, it has an output either drawn from MD or from MD prime. So for every attacker A, we will have some form of true positive rate whenever the attacker guesses correctly. And whenever D prime has been used, but the attacker has guessed that D was used in the input, this will correspond to some form of false positive rate. So we can get some form of empirical lower bound from this, and this corresponds with our empirical epsilon. So we did the same for local differential privacy, And in this case, it corresponds to input value. So it's either V or V prime used in the input of the mechanism. So the distinguisher is trying to distinguish which value has been used. So we formulate LDP as some form of a binary hypothesis testing, where the input has been either V or V prime, and the attacker will either guesses correctly for n guesses as a 2 positive rate, and if the attacker guesses incorrectly whenever V prime has been used but it guesses V, it will correspond to some form of a false positive rate. And in the end, we have the empirical lower bound. So what we proposed is essentially this, which is an LDP auditor. We start with a mechanism. It can be an epsilon LDP mechanism or not. We fix two different inputs, V and V prime, and we run some attack, and we fix the output, for example, to V. So whenever the attacker guesses correctly, we have the true positive. Whenever we use V prime as input and the attacker guesses V, it's a false positive. But a single run will not be good enough because we have a lot of randomness in the mechanism, in the attacker. So we have to done a lot of, because we are trying to statistically measure differential privacy. So these will come up to Monte Carlo methods. So in the end, we will have some true positive rates and false positive rates. And this is used to estimate the empirical privacy epsilon that we have. So I talked about the attacks. So basically, in LDP, we have the user's value uses some form of local differential privacy mechanism and generates C. So the server or the attacker looking only at C and knowing how the mechanism works, it tries to predict what was the input value. So the distinguishability attack we talked before. But the problem is that we have a lot of different LDP mechanisms because they have different encoding, or sometimes they have the same encoding but different perturbation parameters. So it means that the proposed attacks in the literature, they were tailored for the LDP mechanism question. There is no fit at all attacks for this type of thing. It's not like the membership inference attack we have for machine learning algorithm. So here is an example of just two LDP mechanisms. One of them has been used in Google Chrome, which is based, for example, on one-hot encoding, and we have some perturbation of the bits independently. So in the end, the attacker with this information, it will try to predict what was used as input. Or another mechanism, for example, uses some form of local hashing for going from one domain to another domain, and then the attacker, using the information of the bit which has been perturbed to achieve LDP, he or she will try to predict what was used as input. So let's get a sneak peek of our contribution so far. So let's set up, for example, epsilon as a theoretical epsilon equal to, and we have experimented here in this case with 8 fundamental LDP protocols. The names are here, but it just means that they use different encoding and perturbation. So what we found is that sometimes the empirical epsilon for some mechanism was less than 2 times the theoretical 1, or even 4 times the theoretical 1, which means that we get different auditing results because they have different encoding and perturbation, which means different attackability for this LDP mechanism as well. So the only LDP protocol that yielded some form of tight empirical estimation was the well-known randomized response that some of you might know. So some hypothesis that we formulate is that either the state-of-the-art attacks are not strong enough for these protocols, or in some cases where the encodings has some form of randomness, like local hashing, there might be some privacy gain in this encoding instead. So as one of the case study, we have asked if we could use our tool to also detect some form of bugs in state-of-the-art LDP package. So for our lucky, we detected a bug in an LDP Python package, which is called pure LDP, and the LDP protocols which were used were based on one-hot encoding, and they had different perturbation parameters. That's why we had symmetric and optimal linear. So we found that in this orange box, you can see that the empirical epsilon measured was higher than the theoretical one, so this corresponds to an epsilon LDP violation, and we reported the missing step in the codes to the authors, and they already fixed this in their new version. So we have many more case studies in the paper. I invite you to read if you're interested. We also considered, for example, approximated local differential privacy protocols. non-LDP protocols, and also different cases that are interesting for industry, like longitudinal data, collection throughout time, and also multidimensional data when we have several attributes. So, to conclude, what we proposed is some form of a general framework to audit some form of empirical privacy loss for locally differential private protocols. And the main insight is that we not always have a tight empirical estimation. And all these LDP protocols, they differ, so they differ in the attackability, which means they differ also in the auditing. So the findings are generic in the sense that these LDP protocols are building blocks that are used for many tasks, like heavy hitter estimation, marginal estimation, and sometimes machine learning as well. And as perspectives, I invite the community to instantiate this form of LDP auditing to other adversarial approaches that exist in the literature, for example, risks of identification or inference pool, and also extend this LDP auditing to other data or tasks that we did, for example, for mean estimation, that can also be used for federated learning. And we plan to obligate LDP auditor from artifact that I produced it to a general Python package on PyPy. So thank you very much for your attention. And
thank you very much. Questions? Oh, please go ahead.
So the LDP auditor that you have, even if it says that there is no problem, doesn't mean the solution is, the protocol is correct, right? You can't find all the bugs because your LDP auditor is just statistically generating a lot of samples and using a Monte Carlo simulation. Am I correct in my understanding?
yeah, this is exactly the correct insight, because you can see from here that we can detect the bug in high privacy regimes when epsilon is small, because our tool is not specifically for this task of detecting violation. It's just for empirical estimating epsilon. So in some cases there are some tools like a DP sniper in the literature that would find the error for all privacy regimes.
So that was my question. So how does this approach differ from those more robust tools that can detect privacy violations across the entire spectrum of the epsilons?
Sure. So our case is more for the case of we are some firm trying to guess what is the empirical privacy of the LDP mechanisms. We're not trying to find a DP violation or to find the tightness of an LDP mechanism. We're trying to see if you can estimate some form of empirical LDP or some form of empirical epsilon for a given mechanism. But yeah, sure, there are some difference. For example, the literature has specific tools for verifiability of differential privacy guarantees, while our is auditing tightness or empirical privacy guarantees of a mechanism.
Yeah, one more question, please. And the microphone is coming. By the way, we have 2 people standing. Maybe you can help them.
Sebastian Hasler from the University of Stuttgart. It seems that your auditor somehow needs to find good attackers because the theoretical epsilon is the maximum epsilon over all possible attackers, and the empirical epsilon is only the epsilon for some attacker which your tool was able to find. And for me it seems highly non-trivial how you find a good attacker for a generic protocol automatically. So how can you explain how does your tool do this?
Thanks. So this is also a question of ours as well, because we use it what has been proposed in the literature. For example, the attacks for this mechanism corresponds to this attack was proposed in the literature, and different the mechanism, we have different attackabilities. So we don't have a fit-at-all attacks for any LDP mechanism. What we used was existing attacks in the literature. So I'm sorry, but I cannot answer with a completely answer for this.
Okay.
Well, thank you very much. Yeah. invite our third speaker of this session,